And if you're dealing with overtime, you're working 40 hours a week, you get paid $10 an hour, all of a sudden when you get past 40 hours, it goes up to 15 hours, or $15 an hour. You get that time and a half. It changes, the rate changes at some specific part in the domain, the number of hours you have worked. Remember, every time I talk about domain today, I'm talking about X values. Range are always going to be our Y values. So these graphs are only going to be shown for specific values of X, specific domains. So what happens here is that we're going to be looking at what are called piecewise functions. And piecewise functions are nothing more than functions that are written in the combination of multiple equations. Now, you've done this before. You've written multiple equations on the same piece of graph paper. We're going to be needing graph paper over the next few days. So I'm just going to pass out a couple chunks for all the rows. If you guys want to grab 2, 3 pieces, just leave them in your notes. That's fine. And I always have plenty of graph paper. I'll have graph paper in the back by the pencil sharpener in those little trays. I got graph paper up here underneath the computer area. So whenever you need graph paper, just help yourself. So remember, these piecewise functions are written as combinations of equations. These functions are defined by their domain. So yesterday when you guys were doing all of these types of problems, these were all piecewise functions. There's plenty of it going around, so I just handed out chunks. Just like we did yesterday, when we were looking at these when we were looking at just the values, where does the 0 go? Well, the f of 0 applies to this first part of the graph. The x is less than or equal to 2. We would graph that part. When it's greater than 2, we'd add a different line. These graphs are domain specific. So what we do today to start with what this looks like is to start by graphing a line segment. Okay? So I'm going to look at a line segment. Now, these are just the same problems you did yesterday. I'm not worried about writing those down, but I was explaining to you here is that this is the specific area that you would show this graph. This is the specific area of that graph. So those domains will be shown. So what I want to start with is a very, very simple equation. I want to start with y equals 1/2 x plus 4. And we're going to graph it over a specific domain. Now, the easiest way possible to graph these types of functions is to go ahead and plot it like you normally would with slope-intercept form, mx plus b. And anytime that you have something written in slope-intercept form and you're going to graph that, where do you always start your graph? What's my y-intercept here, guys? 4. So here's what I'm going to do. I'm going to start at 4, make a dot. From there, I'm going to walk my slope. My slope is 1/2, so up 1, right 2, up 1, right 2. Exactly. And what I do a lot of times with these types of graphs is I don't connect my lines, I don't connect my dots right away. What I'm doing is just filling the entire grid that I have, that 10 by 10 grid, of the dots that would make up the line. Okay? Now, since I only want to look at this graph for a specific domain, I'm looking at the graph between when x is larger than -5, but smaller than 7. So that means when I go to my axis here, I look at -5. It's right here. Well, the line would be about right here. See how it's not exactly on one of my dots for the slope, but you can all see where it would fall in place? Yeah. Now, when you guys drew inequalities and segments and stuff like that before, do you remember the difference between open and closed dots? Yeah. Is this going to be an open or closed dot there?
Closed.
Why?
Because it's equal to or less greater.
Yeah, exactly. Remember, anytime you have less than or equal to or greater than or equal to, it's a closed dot. If it's just plain old boring less than or plain old boring greater than, it's an open dot. So I'm looking at it for it's larger than -5, but smaller than 7. or equal to. So I'm looking for just this chunk of the segment. What do I do with those dots outside of it?
Get rid of them.
Get rid of them. Goodbye.
Ain't no view.
And that's it. And that's a piece of the graph. It's a line segment. Piecewise functions can be line segments or rays. Remember, arrays have a definite endpoint and it goes infinite through another point. They may change direction more than one time. They may be horizontal. They may be steps, all that kind of stuff. But the way we set these things up is always the same. We start by graphing the line, which you guys all know how to do, walking your slopes, going back and checking where your domain is specific, open or closed dot, and erasing what you don't need. Does that make sense? All right, let's try a couple more then like this. I'm gonna go right to this. Instead of doing another segment, we'll go right to a piece. In this graph here, we have f of x equals x or x minus 1. The specific domain that it's looking at is for the x, if x is less than or equal to 0. And then for the x minus 1, it's when x is greater than 0. So when I go to graph this, I start by graphing the first equation. F of x equals x. What's my slope? What's my y-intercept?
0,
0. Good. So I start at 0. I just walk my slope of 1. Go the other way. And these first few examples, I might be a little bit over zealous in filling in the entire grid. And over time, you'll start to see that you don't need to. Now, I only want to show that line for when x is less than or equal to 0. So I go to my domain at x equals 0. And will that be a solid or an open dot?
Solid.
Solid again because of the equal bar. And which way, going down and left or up and right, are the ones that are going to be less than or equal to 0?
Down.
Yeah. Going towards the left. And then what do I do again with the other ones?
Leave them
And they're gone. What's that? It's weird, but it's telling you it only wants to look at the graph when it's less than or equal to 0. Well, there it is, less than or equal to 0. And if you remember from geometry last year, this is a ray. It has an endpoint and it goes infinitely through another whole other sets of points. Now I just graph the other one. The other one is x minus 1. Where does that one start?
Minus 1.
And what's my slope again? 1. I go back to the 0 value. For this graph, is that going to be an open or closed dot at 0? It's open. So I might just do this. Just draw a big circle around it. And that's fine with me. Or you can erase it and draw an open circle there. And I don't have to go this direction with the graph because I've already covered that with this domain. This domain is specific for being greater than 0. What's that? No, I have it purple. Green doesn't show up very well. I can change the colors. I can make it white too, red line. It's pretty cool because if you do like a real dark background, you can put white so it looks like I'm writing on a chalkboard.
Do it. You can do it.
Not now. Undecided.
Tomorrow.
Tomorrow, maybe. Okay?
Break Murphyno. Why not? Just think it over. It's a great name.
I've thought it over, and we say no.
Okay.
Let's try another one. F of x is 2x minus 1 when x is less than or equal to 1, or f of x is 3x plus 1 if x is greater than 1. So the specific domain that I'm worrying about here happens, something occurs around x equaling 1. Once again, when we go to graph these, the very first thing that we're going to do is just use it as y equals mx plus b. And 2x minus 1, I start that at
-1.
-1, and walk your slope of 2. Up to right 1. And down and left. I'm only worried about this graph when it's smaller than or equal to 1 for the domain. So I look at the value at 1. I already have a dot there, which is good. Does it stay solid, or do I make that an open dot? Stays solid. And I want values that are less than or equal to 1, so I'm going to the left. Never said I could draw a straight line. What do I used to?
No, I can never draw a straight line either. So.
And then I do the same thing with 3x plus 1. Start at positive 1 and walk your slope of 3.
A little stretch.
I'm not going to bother with moving this one to the left at all, because the domain has already told me that it's been taken care of with the less than or equal to 1. So now I just look at what happens at 1. Is it open or closed?
Open.
It's open.
Open.
So I'm going to make this a little bit of an open dot, erase that one there. To make you happy, straight line.
That's so big. It's not
You know, complain. Jeez Louise. Stuff I got to deal with. No.
That's so small.
Too skinny.
See, there's just no making anybody happy.
Nope. That's perfect.
All right.
Why would you just go to the one that actually with the arrow?
So as you can see, what's happening here, guys, when we're looking at these graphs, the graphs themselves, y equals mx plus b. It's stuff that you guys have all done many times. The only thing that's new about this now is this domain part, the domain specific for the piecewise function. You're graphing two equations on one grid, and you only want certain parts of the graphs shown. Okay? I believe the next one I have is a little bit more specific. I think we used this numerical version of this one yesterday. This one gets a little bit trickier.
It's a little passy.
Well, it's not so much that you're looking at in between, x values in between of a domain area. So you have to figure out what are the chunks that you're having to graph. So you still graph them like you would normally. And then it's just a little bit longer of a time to figure out what you have to erase. So I have f of x is 2x plus 1, or it's negative x. My specific domain areas are at x is between negative 2 and 6, with both of those being open dots because they're both less than it. And the other domain specific areas between negative 8 and negative 4. Once again, open dots on both of them because there's no equal sign. We'll be in agreement on that.
Yep.
All right. So all we do now is just plot. We walk through, start at 1, walk the slope of 2.
Oh, we're doing this one first.
Okay? I'm looking at my domain between negative 2 and positive 6. So in this graph, I figure out where negative 2 is. It's here. This becomes an open dot. And then positive 6, so happens to be a little bit off my grid, so we'll call it up here.
Okay.
And there's that part. And now I graph the other one. I graph the other line, which is negative x. And I want that to be between -8 and -4.
Wait,
Waiting.
the mouth threw me out. Alright. So x has to be greater than -2 but less than 6.
Yep.
So would you erase that top part of that?
This is +6. Way up here, it just so happens it just didn't fit on my grid, that's all.
Wait, isn't that 10 though? Up there.
That's the range. This is the range. Range are your y values, your x values are your domain.
That's all right, Michael.
So these are what I'm looking at. I'm looking at my specific domains, my values of
Alright,
x. So these are the x, this is the x-axis here.
Ah, yep.
Okay?
Gotcha.
Does that make sense?
Yep, yep.
That happens a
Took
lot.
me a
People
while.
mix them up. It's not the end of the world. Just don't do it again.
Oh, that was the X value.
Do the exact same thing with the negative x value. Walk my slope.
Yeah.
And I want that to be between -8 and -4. Here's -4.
It goes bottom right.
Yeah.
Oh, yeah, I'm sorry.
I was gonna say it, but I didn't want to look stupid.
Yeah.
No, you're okay. You were paying attention, way to go. I never make mistakes.
Yeah, Seth said that.
And once, yes, Seth said that a lot, right? And once again, just go back to your domain values of -8 and -4. And that's what your graph will look like. That's it. It is. It really isn't all that difficult. What's different here is that you have to stop and think, where do you have to erase? Where do you have to fill in dots? Where do you keep things open? It becomes, like I keep saying, very domain specific. So I've got a couple funkier ones for you guys to try. And I've got these things on a separate worksheet. And I wanted to show you how you can do some of this stuff with your calculators as well to help you guys with some of the table stuff. Okay. What's that? No. Instead of trying to get you guys to keep continuously writing and drawing graphs, I took the time to just kind of make something up to help with notes and whatnot.
Thank you very much.
It's just notes.
Is our homework harder?
Jesse, come on now.
So what I want to do here is look at where we're at. On this very first problem, you've got two graphs. You've got two graphs to worry about. You've got x plus 5 and x squared plus 2x plus 3. But what I want to do now is remind you guys how you use your table function on your calculator. So please, 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 take out your calculator real quick. And what I want to do is start with the first one, x plus 5. Remember, all you have to do is go to your y equals button and type in x plus 5. And then go right away to your table, second graph. Everybody got that all right?
Yeah.
Now, in this case here, your table might be a little bit different setup than mine. Your table might start at 0. What I would do is just scroll up a couple of buttons so that it starts maybe at -3. Because what happens then is that you've got a nice range of positive and negative values for that graph. Because what you have now in front of you are all of the ordered pairs that you would plot. All of your ordered pairs are right there. I know that if I take these ordered pairs, that's really cool. Thank you. I know that if I take these ordered pairs, x is -4, y is 1. -3, 2. -2, 3. And so on. What the calculator is giving me with that table, obviously this example, x plus 5, I know that all of you guys can draw without too much of a hassle, unless you forget what a positive slope looks like. I forgot what a negative slope was. You're able to get the table, and you should never get those points wrong. Okay? Now, to be specific with this graph then, what do I have to look for? What's my domain specific? At -2, when x is -2. At x, -2, x is less than -2. Will that be an open or closed dot when x is -2?
Open.
Open, very good. So I go to -2, and I make sure that this dot becomes an open dot. Does that mean I'm going to the left or to the right for connecting it?
Left.
Correct. And then I just erase the rest.
How do you want it to go?
I'm looking for numbers that are smaller than
Oh,
-2.
okay.
Remember, the graph could be pointing down to the left, it could be going up and left. It's just you're looking at going this direction, that's all.
Are you gonna take off for not putting the arrow right there?
No, because I'll forget half the time.
Okay.
All right. One thing I didn't tell you on this grid, I forgot to use my 10 by 10 that actually had some numbers written on it. I'm assuming you guys all counted by ones.
Yes.
On a good day. On a good day, yeah. Now I do the same thing with the quadratic. Now, we all remember how to graph quadratics, right? Opposite of b over 2a gives you your axis of symmetry, and then you plot symmetrical twins and have a lot of fun, right?
No, I've never.
No. Silly, silly children. Y equals. Clear out what you just did. What was it? X squared
Plus 3x, 2x.
2x
Yeah.
plus 3.
Yeah.
Bada bing, bada boom. Table, and voila.
Dude, that's
There are all of your ordered pairs.
My life has just been.
I'm telling you, the table function is a savior for so many things.
Yes.
When you do function notation, when you do direct substitution problems, everything like that, use the table because it alleviates making the mistake of substituting a -4 and squaring it. Yes, sir.
So just for like all problems like this, you can just use the table.
Absolutely. That's the whole idea. I mean, I'm hoping that you don't have to use a table for x plus 5.
Yeah.
But if you've got a quadratic in there, go for it. You know, some of the ones that I've shown earlier, because I wanted to show you guys that you can use your table to help you get the right ordered pairs and make sure that your graph is correct. So I'm looking at my domain, and my domain has to be specific at x is greater than or equal to -2. So do I care about what's happening at -4 for x? I don't care about anything until I get to -2. And what's the ordered pair at -2? -2 and 3. Now, we have a bit of a predicament.
Yeah, you can't really draw that straight.
Because take a look what happened. They're sharing the same point, aren't they?
Yeah.
Now, that's okay. There's nothing wrong with that. And I'll show you why here in a second. Let's continue. The next one was it goes down, goes back up, and then it's at 1, 6, and then it's off the graph. So it makes a curve.
0, 1, 2, 3.
What's happening? Oh, scrunchy face. You all right? It curved down and up. It's part of the parabola. Remember, it's a parabola, it's quadratic, so it's a parabola. It's just part of it. And the other part's a line. So what happens here is that sometimes it's perfectly fine for the intersection of the two graphs to occur where this happens. It just means this domain-specific area, if it's -2 or greater, it's on the curve. If it's less than -2, it's linear. That's all it's saying. And it's okay that they happen to, the graphs happen to overlap like that. There is nothing wrong with that. You can't draw an open and a closed dot at the same time. You just make it a closed dot, and then you fall back upon your domain-specific area. Okay? Does that make sense? and it's usually written like that, where the smaller value is when you write it out backwards, which we'll probably wind up doing tomorrow, you'll start with the less than symbol and then switch it over to the greater than as it's going up, as it's increasing. It's not fun. Not very scary, is it?
Is it gonna get scary?
You never know.
Yeah.
It's kind of.
Let's try another one. Take a minute or two and try this one. As you go through these things, your two equations, 2x plus 1. Once again, start at 1, up to right 1, down to left 1. I'm looking for all values that are for the domain greater than or equal to 1. So I start at the value of x of 1. This is a solid dot, and I want to be greater, so I got to go to the right. I'll erase the rest. For the other one, it's x squared plus 3. I'm going to do this without a calculator. If it's at 0, x is 0, y is 4. If x is 0, y is 3. If x is 1, y is 4. Good. And now this has to be an open dot because it's less than 1. If x is negative 1, it is also at 4. If x is negative 2, it is at 7. So here's 4, 5, 6, 7, and there's my curve. Like that. There's a jump in there. There's a jump in continuity. It overlaps a little bit weird. It's on that loop. It's playing, was it Line Rider? You had the Snowball Express and you jump over stuff. It's doing that. All right. We did not have enough time to go through and finish some more of these examples, nor did we have enough time to write equations from these yet. I believe there are only 4 more of these for you to do. Please do so. We'll go over those tomorrow. All right? The last 4. There's 4 more on here. The graph and yeah, don't worry about the function notation parts on the last 4. What I want you to do are the graphs of the last 4 problems on that sheet.
Regular TIA
Should do.
Why?
What's that?